All right, so your TA Indiana is looking pretty sleepy down here, but maybe you'll stay awake long enough to help us out with this fluid mechanics manometer problem. We'll start off with a super fast mini lecture about pressure, density, specific weight, and specific gravity. Then we'll use the given pressure on one side of the manometer to find for pressure on the other side. And the tricky part about this problem is going to be that one of the fluids in this manometer is actually a gas. So we've got an air bubble trapped inside. And while it may seem tricky, it's actually super easy. You'll get it no problem. All right, your TA is so close to falling asleep. It's like he's going to pass out any second now. So I start off every problem with given, find, concept, assumptions, and solution. If you've taken my classes before, assumptions might be kind of new. In your junior and senior level engineering courses, you're going to find a lot more equations are only applicable in certain circumstances, and so a required part of your education is to show that you recognize which situations you can use these equations. And also, some problems are just either too complicated to solve or you're not given all of the information that you need. So for all of these cases, you're going to have to mark down what assumptions you're making in order to finish the problem. So to start off by looking at this picture, it may help to look at this at kind of a 3D perspective to get an idea of even what you're looking at. The circles at A and B are not actually circles. Those are just cross sections of a pipe. So the purpose of this style of manometer would be to compare the pressures of these two pipes that both have fluid flowing through them. Now, pipes do have very complicated flow, so we're ignoring all of the actual flow, whether it's turbulent or laminar, what the pressure distribution is inside. You'll come back to that in a later chapter. So for this problem, we're given the pressure at point A, 15 psi, and we're trying to find pressure at point B, which I'm going to label PB, which also has to be in psi. The main concept for this problem is manometers, or hydrostatic equilibrium, or just go ahead and write down the equation itself. Delta P equals rho GH, where rho represents the density. It's going to be a mass divided by volume, like kilograms per meters cubed or slugs per feet cubed. Two other ways you'll see this equation represented is specific weight times H. Since density and gravity are so commonly used together, their combination is specific weight, which instead of mass per volume is force per volume, like newtons per meters cubed or pound force per feet cubed, pound force per inches cubed. And the third version you may see is specific gravity of your fluid times the density of water times gravity times height. So a lot of tables where you would try to look up density might actually show specific gravity. And specific gravity is a ratio as to how much more dense or less dense your fluid is as compared to water. So the specific gravity of water is 1, meaning it has the same density as itself. Heavier fluids like mercury that are very dense would have a specific gravity greater than 1. And then fluids that are less dense than water, like oil, they'll have a specific gravity less than 1. All right, the assumption section on my page, I'm going to start off with that blank, and then as I solve the problem, every time I make an assumption, I'll go back and write it in there. So before we apply numbers to the problem, let's understand the hydrostatic equation itself. When you think of pressure in liquids, what I want you to think of is weight. So imagine that you dive down to the bottom of a swimming pool and you look up and you see a column of water all above you. That water is pushing down, and as it pushes down, it's squeezing in on you from all sides. Now, the taller that column up above you is, the more weight of water is pushing down. And then the amount of force that it actually applies is based on surface area. The expression rho GH, rho times G, density times gravity, that is the units of force per volume. So once you multiply by the volume of the liquid up above you, you'll know how much force is pushing down, how much it weighs. So H multiplies by height. So if I'm 6 feet underwater, I've got 6 feet up above me. That leaves me with units of force divided by area, and that's pressure. And if I knew what that area was, I could multiply pressure times this area and get the amount of force. So the term pressure is really useful because then we can apply it to any surface area. If we wanted to find the pressure on the bottom of the pool, we can multiply by the area of the entire bottom of the swimming pool. Or if this is some fancy pool with some window over on the side, we can find the amount of force on that window by just multiplying by the size of the window. So as we look through this manometer problem, every time the fluid goes downwards, we're going to increase pressure Every time the fluid bends and comes back upwards, we're going to decrease pressure. So looking at the problem, I've got point A on the left, point B on the right. So I labeled points 1, 2, 3, 4, 5, 6, where everything sort of interesting is happening. And we're just going to go point to point and hop our way through the problem. So point 1 is going to be the pressure at point A plus rho GH. So the first assumptions whenever you use this manometer equation that you have to always write down is 1, that your fluids are incompressible. Rho GH can only work if rho is constant. If density is changing throughout your liquid, then that's going to throw off all the calculations. The second assumption is going to be that all velocities are 0. This is the hydrostatic equilibrium equation. It does not work for moving liquids. If your liquids are flowing, then you'll need to probably use the Bernoulli equation, which accounts for velocity. You'll see that in probably the next chapter you get to. So to find my specific gravities, I'm going to go online to the engineer's toolbox, but you may have a table of these inside your textbook also. So for fuel oil, it gives me a range of values. I'll choose a value right in the middle, 0.885. I'm writing the properties of this liquid under the givens. So for English units, the density of water is 1.94 slugs per feet cubed. Slugs is a great unit. I hate using it so much, but it really just makes me laugh every single time. Before I multiply it out, I can already see that the units are going to be a problem because all of my heights on the drawing are in inches. So I need to convert this density of water into inches instead of feet. So dividing by 12 cubed to get 0.001123 slugs per inches cubed. So now the pressure I started with, 15 psi plus 0.885 specific gravity times 0.001123 slugs per inches cubed times gravity, 32.2 feet per second squared, not 9.81 because that's meters per second squared, times the total 22 inches of height from point A to point 1, and that gives us a total of 15.704 psi. This manometer equation can only be used to compare heights within the same fluid. That's why I had to stop at point 1. I can't go any further than that because at point 1 the fluid changes, and when the fluid changes, the density changes, rho. So when you have a manometer with different liquids, you have to do a different use of the manometer equation for each different liquid. So now from point 1 to point 2, I'm using mercury, but the equation is still going to be the same. I'm starting off with the pressure at point 1 and adding rho GH, or in this case, the specific gravity of mercury, times density of water, gravity, and the height difference, which in this case is 6 inches. Plugging in these numbers, I get to a pressure of 18.64 psi at point 2, which is in the middle of the mercury. Now you may be wondering, why didn't I go all the way to point 3? From point 1 to point 3 is all one continuous liquid, and so I could have done that. But there's actually no reason to. From point 2 to point 3, we go down through mercury, but then from point 3 to point 4, we come back up through mercury. So if we had done both of those steps, we would have added pressure due to 6 inches of mercury, and then subtracted pressure due to 6 inches of mercury. And that would have just canceled itself out. So whenever you have these U-turns with a single continuous fluid, you can just go from the height at the start of your fluid to the height at the end of your fluid. And so the pressure at point 2 that I already calculated is exactly the same as the pressure at point 4, which is the pressure that I need at the interface between the two liquids. So the pressure at point 4 is also 18.64 psi. So now from point 4 to point 5, we're in SAE 30 oil, and pressure is going to be decreasing because we're getting shallower, so there's less weight pushing down. So the same online table, I can look up specific gravity for this SAE 30 oil. It gives me a range of values, so I'll just pick a value in the middle. So we've got the pressure at point 4, plus the specific gravity of our SAE 30 oil, times density of water, times gravity, times this height of 18 inches. And now we're up to a density of 18.05 psi at point 5. And now at this interface, there's an air bubble. However, the density of a gas is approximately 0. It weighs almost nothing over small scale air bubbles. So in order to use the manometer equation at all, you have to assume that all of your fluids are incompressible, that density is not changing. And let's just go ahead and assume that the density of air is 0. It's going to be negligible. And what that's going to mean is that the change in pressure between 0.5 and 0.6 is going to be 0. And that makes sense. For air, for gases, we assume that they exert the same pressure at every point in the gas. At both ends of the gas are going to be the same pressure. So point 6 is still at 18.05 psi. To go then from point 6 to point B, we just add that weight of 2 inches of SAE 30 oil. So it's the 18.05 plus specific gravity of that oil, density of water, gravity, and this 2 inches of height. And again, we're adding, since at this point we're going downwards from point 6 to point B. And we get a final answer for the pressured point B, 18.12 psi. The next 2 manometer videos in this series, one is going to include a piston and you'll have to solve for force instead of pressure. And then the other is going to look at an inclined manometer. What happens if the tubes are actually running diagonally instead of vertically?